And I want to tell you about the combinatorial aspects behind a recent proof of a formula for the top-weight Euler characteristic of MGN that was obtained in joint work with Faber, Galetius, and Payne. One of my reasons for de-emphasizing the geometry is that, first of all, the combinatorics is quite fun. And also the geometry has been covered quite well already in other parts of this summer school. For example, in the lectures of Margarita Mello last week, and also the Stagosaur learning seminar on the top weight cohomology of MG. So here I will try to work with fairly few prerequisites. I tried to specify them in the abstract. For the first lecture, it will be helpful to have seen representations, finite dimensional representations of symmetric groups. And in the second lecture, knowing the definitions of categories and functors will be helpful. Okay, let's get started. Oh, and please do ask questions in the chat. They really help me stay grounded when I teach. Okay, let's start with the combinatorics of graphs. So the first thing I'd like to do is to define what a graph is for me. So usually one draws pictures of graphs like this, say. Let me define it like this. So it's the data of finite sets, V of G and H of G. These are called vertices and half edges. The set of vertices of G and the set of half edges of G, respectively. And the data of how these all glue together. So first of all, a map, which is a fixed point free involution on half edges. I'll call my map S. And a map R that I'll think of as a root map. That's just my private terminology. That assigns a vertex to every half edge. And now you can try to make this definition agree with maybe a previous definition you may have had of a graph in your head. So in this graph, you see I have 2 vertices, 6 half edges. And I'll try to draw a little notation here. So if this is the half edge H, then its pair S of H is the other half edge, so to speak. Here is R of H, its root, and here is R of S of H. I haven't yet defined the edge set of a graph, but here it is. It's just the set of equivalence classes, 2-element equivalence classes of half edges under the involution S. So we take H and identify it with S of H, and this is called the edge set. So in our running example here, we have 3 edges. And that's a graph. Is it okay? It's not the way a graph theorist would typically define it, but this is right for us. And in particular, this is right for our geometric applications. For example, in last week's lectures, you saw that one could associate a stratum of compactified moduli space of curves to a graph. And this definition has the right notion of automorphism. Actually, that's the next thing I should say. So an isomorphism of a graph, say from G to G prime, well, it's sort of what you would expect. So it should be a bijection from vertices to vertices and half edges to half edges that's compatible with the involution and with the root map. So maybe I'll just write briefly what it is. So it's a renaming of all the data of G to the data of G prime. So it's a bijection from V of G to V of G prime, and a bijection from H of G to H of G prime. And I'll just write maybe compatible with the gluing data. So S, the maps S and S prime and R and R prime. Okay? Everyone good so far? All right, so let me turn the page. So definition and n marking. So fix some non-negative integer n, then n marking on a graph is but a function m that sends 1 through n to the set of vertices. So you're just marking the vertices. Could be surjective, might not be, could be injective, might not be. This is just a marking function. And we'll say that a pair, so a marked graph, in other words, a pair G comma M is stable if for every vertex, basically that vertex has a topological reason to exist. So the number of half edges at that vertex, which is detected by R inverse of V, plus the number of marked points at that vertex, which is detected by the set M inverse of V, is at least 3. That's what stable means. And of course, the motivation for this definition and for the choice of terminology is from what you may have seen in last week's lectures or in Stagisar. So these are a subset of those dual graphs that are dual to stable curves with n marked points. I should also define genus actually in the same vein. So we say that GM is connected and of genus G if its geometric realization is connected. So if, when you realize it as a CW complex in the way that was sketched in the example in the previous page, if its geometric realization is just connected as a CW complex, as a topological space, and has chi Euler characteristic 1 minus G. This is equivalently phrased as the following purely combinatorial calculation, that the number of edges minus the number of vertices plus 1 equals G, as you may check. Okay? So for example, sorry, are there any questions? Please let me know. That's exactly right, yes. So if I were defining things, if I were including all dual graphs of all stable curves of type Gn, then there would be a vertex way, a weight function on the vertex. And I'm restricting myself to this locus because of implicitly a proposition that I'm using in the background, which will say that for my purposes, for the purposes of calculating things about the top weight cohomology of MGN, or equivalently of graph complexes, the curves with, or the dual graphs with positive weight vertices don't contribute. And that's a thanks, Diane, for the admonishment. I should repeat the question. So Vance asked, from the dual graph point of view, these are dual graphs whose curves only have rational components. That is correct. So this is the analog of every vertex having weight 0 in maybe a broader context that you may have seen in other talks. And this is the analog of the case in which, yeah, so these are exactly dual graphs in which every component is isomorphic to a P1. Okay, have I answered the question? Great, okay. Thanks for asking. So let me do a quick example. Let's draw the finitely many isomorphism classes of connected stable graphs of type G comma n equals, say, 1, 2. So here I mean genus 1 with 2 marked points, And this will also just be an introduction to how people draw these things sometimes. So here's one. It has two vertices, two edges, one of which is a loop. And here I'm drawing the marking function as is typically done. So this is, you can draw the markings as sort of phantom half edges. So here we're just saying that m of 1 equals m of 2 equals v. Yeah, and this thing's connected, as you can see. And it's stable because each vertex sees three things at it, basically. Is that okay? So this is one of them. And here's another. And here's another. And I think this is it, actually, up to isomorphism. And these three isomorphism classes are organized in a poset under the relation of edge contraction. Do you know what edge contraction is? It's the relationship in which if you have an edge in a graph that's not a loop, then you can shrink it to length 0 and identify its endpoints. So in this way, the set becomes a poset. And it's even, one can sort of promote that poset to a better category, which remembers the actual map, the way in which you identify the contracted graph with the result. Yes, let's see. Are markings related to the legs from last week? Ah, yes, it's a synonym. I think people use different terminology for the same thing. Great, thanks. Thanks for the question. Any others? Okay. So let me leave as an exercise. I didn't write this in the exercise sheet, but let's just frame as an exercise that there are only finitely many isomorphism classes of marked graphs of type Gn. So you can see an example of that calculation above in the poset. And this is an Euler characteristic calculation that you can carry out. Great question from Madeline. Is the number of half edges at V twice the degree at that vertex? I think it's exactly the degree. So I think my answer, Madeline, is that R inverse of V is exactly the set of half edges touching the vertex V. So in our example up here, each of these, okay, so this vertex has, 2 half edges at it. This vertex has 4 half edges at it. But it's true that loops contribute twice to the degree at the vertex at which the loop is based, which is maybe what you are asking. Does that resolve your query? Okay, awesome. Great, anything else? Thanks for asking. So the question is the total number of isomorphism classes of fixed G, N known? I think not. I think not. So in complete generality, no. Let me tell you, okay, so yeah, you anticipate what I wanted to say. Yeah, the minute a combinatorialist tells you there's finitely many blahs, you should ask how many. We're about to refine that. I'm about to make a case that that question should be refined in a particular way. But for, the first question is, well, how many are there? I think that the answer as such is not known. When G equals 0, you can say more. So this is this is just the count, or this is the count of the strata, the boundary strata of M0 and bar. So when G equals 0, you can say a lot. The number of isomorphism classes for n equals 3, 4, 5, and so on. Note I'm starting at 3 because that's when these sets are non-empty. It's the following lovely sequence. You can see the full sequence in the notes. I will only write out the first few terms. And this is OEIS. This is the online, what is this? The online encyclopedia of integer sequences. it's well known there are recursive formulas and so on. And this is related, by the way, this is the same as the count of so-called phylogenetic trees on n-1 taxa. And you can see the work of Valera Holmes Voetman for the connection here. In generality, in complete generality, I don't know the answer to Vance's question. I think that the answer is really not known. So for example, you might fix n equals 0 and just ask, like, how many stable connected graphs are there of genus 2, of genus 3, of genus 4, and so on, right? There are 0 when the genus is 0 or 1, I should mention. And here, I can tell you how the sequence starts at 7, 42, 379, 4,555. So again, this is the number of, oh, sorry. This is a slightly different count in which, let me just temporarily allow weights on the vertices and count all stable dual graphs of type Gn. Sorry, so this is a related count. Yeah, so for example, this 4,555 is the number of boundary strata of M5 bar, the number of topological boundary strata of M5 bar, and so on. So this is sequence OEIS 174,224. So this sequence actually references my thesis in which I computed some of these numbers, and there's great software by Maggiello Pagani computing this and many more numbers. Okay. Yeah, okay, great. So that is the right question, you know, how many of these things are there, given that there are finitely many? But a perhaps more interesting, more geometrically relevant is an orbifold count. That's going to be the theme of the last part of lecture 2. And in particular, the so-called orbifold Euler characteristic of a certain graph complex built on these graphs is going to be, has great geometric significance and was closely related to this formula for the top weight Euler characteristic of MGN that I've been alluding to. So that's where we're going. Sorry, is this transitional sentence okay? So what I'm saying is that this is a good hard problem, but a related problem that, roughly speaking, takes automorphisms into consideration, is going to be closely related to a geometric formula, and I'm now going to beef up the combinatorics, defining a graph complex, so-called, of graphs of genus G of n marked points. Okay so far? Questions? Sorry, let me turn my phone off. Okay, so let's go to section 2. So Konsevich's graph complexes. A word of warning right away, which is that there are lots of different versions exposed in, you know, multiple papers of Konsevich. So I'm going to be studying a particular one. It's known as the basic graph complex, or it's closely related to the commutative graph complex. All right, so for this entire theory to be non-empty, or to have any hope of being non-empty, let's fix integers g and n with 2g minus 2 plus n positive. And my next goal is to define a rational chain complex. So chain complex, finite chain complex over Q. I'll write it G upper little g n. And it's an n-marked version of Konsevich's graph complex, G upper G. And I'll tell you what it is. So let me just tell you what is it in degree P. Namely, I need to tell you a vector space, G upper Gn sub P. So this is a Q vector space with generators G, M, omega, where Gm is a gadget that we've encountered before. This is any connected n-marked, and loopless. I'm going to both underline that and put that in parentheses.
Did you switch M and N? What is M?
Sorry, M here, thanks for the question, Tyler. So M is the n marking function. So this GM, you should think of it as like, you know, one of the 3 gadgets that we drew, for example, several slides ago. Is that okay?
Mm-hmm.
Okay, thanks for the question. Okay, well, sorry, let me finish this sentence. So we take all connected n-marked loopless stable graphs of genus G. So this loopless thing, so you can allow loops or you can disallow them, and it's a non-trivial proposition that the results will be the same. So in order to make some of the exercises in the exercise session just a little less painful, I've decided to prohibit loops. Is that okay? So this would be, what is this? What is the geometric analog of this? I think it is not allowing any, requiring all the components of the corresponding stable curve to be smooth. Okay. So I haven't told you what omega is. Omega here is simply an ordering of the edge set. More precisely, a bijection from the edge set to the set 0 through P. Okay, so it looks like just one of the gadgets that, you know, we drew in the previous slide, but you just number the edges 0, 1, 2, and so on. And the degree that this generator lands in, it lands in degree P if there are exactly P plus 1 edges. Is it okay? So these are the generators, and now I have to tell you relations. So ... let me flip the slide. Right, I had better tell you relations, because like I promised you a finite chain complex. And right now, at least being very formal, I have, you know, uncountably many generators or something. You know, I haven't said anything about isomorphism classes. So far, I just have one generator for every single genus G n-marked stable connected graph. So the relations are as follows. Whenever there is an isomorphism between Gm and G prime M prime, then we obtain a relation of the following form. So here, we suppose we have an isomorphism from Gm to G prime M prime, maybe F, that relates the ordering of the edges of G and the ordering of the edges of G prime by a permutation sigma. I could write this as a commutative square, but I'm just going to write it in English. So omega and omega prime are related by permutation sigma. This is a permutation of the numbers 0 through P. And that's, okay, so that's the definition of the vector space, Gn sub P. You know, let me just try to do an example, because this is fairly, let's see. Let's try to pick up the running example. So this was G comma N equals 1, 2, I think, from last time. So I think I drew these gadgets a couple slides ago. Is that okay? Oh, sorry, what am I drawing? Okay, so right now I have drawn the isomorphism classes. I'm trying to draw what the generators of G upper 1, 2 sub, I guess 1 might be, because these are the things with type G, type 1, 2, and exactly 2 edges. Now here, the generators up to isomorphism look like, well, this left-hand picture or this right-hand picture, together with an ordering of the edges. like maybe this.
Can I ask why you didn't include that third one?
Yes. Oh, two good questions. Okay, I didn't include the third one because right now I'm breaking up my vector space by homological degree. So I'm only looking at the ones with exactly two edges. However, there's an excellent point in the comments, which is I'm getting my conventions mixed up. So I shouldn't have included this one because we actually can just throw out anything with a loop. Thank you. Thank you, Anna. Okay. So actually, I'm gonna claim that this vector space is trivial. I haven't claimed it to you yet, but the point is that so far we threw out the thing with the loop, so we only have one generator left. And furthermore, I claim that the relation that I'm starring just now identifies this generator with its negative, which means that it's 0 over Q. Because you can see that there is an involution, there's an isomorphism from this marked graph with labels 0 on top and 1 on bottom, with the sign of, I don't know how to write this now, 0 to 1, 1 to 0, times this same marked graph with the labels inverted. But of course, this thing on the right is the same thing as this thing on the left. So that says that this generator is killed since the sign of a transposition is -1. Okay, so this is a bit of an odd example to do for you. There'll be better examples in the exercises. Yes. The geometric interpretation of sigma, if we think of these graphs as dual graphs and the edges as nodes. Yeah, okay, so it's an ordering of the nodes in a dual graph. But why would you want to do that? I have to refer to Stagosaur, I think, for sort of more of the geometric background. Roughly speaking, it's been really useful. You know what? I think I'm getting ahead of myself. Let me try to punt your question, Vince, to a bit later when I try to wave my hands just a little bit about why studying this graph complex is related at all to the top-weight cohomology of MGN. Okay, great. Okay, what have I done so far? I think I promised that I was gonna tell you a graph complex. So far, I've told you a graded vector space. So it remains for me to tell you what the differential is. And I won't emphasize this because most of this talk is about Euler characteristic, which is exactly the situation where you can blithely forget the differential. The differential is a signed sum of edge contractions. So I'll write it like this. If you have a generator, GM omega, then its boundary, by definition, is the sum over all I. So let me say that this thing is in degree, homological degree P. So it's the sum, the signed sum of the contraction by edge EI. I'll just write M sub EI and omega sub, maybe just contracted by EI. Sorry, it's a bit of made up notation. So this means the thing you get by contracting. So G slash EI is the contraction of G along edge EI, where EI is the, by definition, it's the edge marked I according to the ordering omega. So it's omega inverse of I. Okay? So I should say that, let's see. Oh no, this is fine, this is fine, okay. Okay, so what are the things, you don't have to worry too much about the differential. There'll be a few exercises on it if you're interested in needing it more. I think one thing to assert is that its square is 0. This is true. And you can do it as an exercise. It's just a matter of signs. And the other thing to assert, I guess just by observation, is that it really is of degree -1 as a map of graded vector spaces, just simply because I'm killing one edge when I contract. So if I was in homological degree P, then now I'm in homological degree P -1. Is it okay? Oh, yeah, that's right. So if you introduce, okay. So it turns out that you will never introduce a loop, I claim. But, sorry, let me start again with Diane's admonishment in mind. The question was, well, what do you do if you introduce a loop when contracting? So the easiest blanket statement I can give you in response is just set it to 0. The second thing to say is, how would you have introduced a loop? The only way to introduce a loop by a single edge contraction is to contract one of 2 parallel edges. Do you agree? But I claim that if a graph has parallel edges, then its class was 0 in the graph complex. Essentially because of this calculation that we did up here in this example. Anytime you have parallel edges, then your graph has what's called non-alternating automorphisms. If your graph ever has an automorphism under which the edge set experiences a permutation of sign -1, then this exact calculation, or its analog, shows that the class of the graph is 0 in the graph complex. Aaron, why are the graphs I am drawing considered as having 2 edges instead of 4? Are the legs not considered edges? Yes, I see that there's maybe some terminology change from last week to this week. So for me, these legs are not anything but just a way to notate that formally I sent the number 1 to this vertex, say, and formally I sent the number 2 to this vertex. So they're not considered edges, but rather the edge set is literally the set of equivalence classes of half edges under the involution S. So in this example, I have exactly 4 half edges and 2 edges. Okay, hopefully that answers Aaron's question. Okay, Alessio says, can you repeat which object this differential is associated to? Right, okay. Actually, I'm not sure exactly what's being asked, so let me just try to clarify. All right, so on a previous page, I said I was gonna introduce a chain complex. So that chain complex is G upper Gn together with a differential partial. So this is supposed to be, so what does that mean? It's a Z-graded vector space, GGN, a finite dimension, together with a differential of degree -1, so it's of degree -1 and a square root 0. So my goal here was to tell you briefly what the differential is, just in terms of its definition. And I told it to you by telling you what it does on an arbitrary generator. Does that answer your question? Okay, let me know if not. Okay, great. Okay.
Melody, there's a question about this notation M mod EI.
Oh yeah, this is notation for the contraction of G along an edge. So let's see. I guess I'm gonna maybe reveal, okay, here, I have an idea. So let me do an example, since I think that I haven't explained this adequately. So here's an example. So here is a, what is this? Sorry, I'm doing this example on the fly. So here G comma N is 2, 2. I have 2 marked points in genus G, genus 2. This is a stable connected graph. And let me make it a generator by introducing, as you can tell, I'm making this up on the fly. So it's an arbitrary, it's just picked an edge ordering here, omega. So the blue here is the data of omega, which is a map from the edges to, in this case, 0 through 4. Did I get that right? I think I have 5 edges here. Okay, so here I have given you now the data of G, M, and omega. G and M were given in the picture. I hope that's okay. And so what is this contraction? Okay, let me just draw the contraction by E naught. So what do? You look at the edge labeled 0, and you shrink it down, identifying the endpoints. So imagine that it shrinks to length 0. So, and I have to draw this thing. Sorry, let's see. I think it looks like this. And yeah, I should have maybe written in my sort of temporary notation, what do I mean? Okay, this is bad notation. Okay, so I'm defining a new graph obtained, a new triple graph, marking function, ordering obtained by contracting E naught. Sorry, it's sort of bad notation. And I do it by contracting the 0th edge. I renumber in order. So now I have 0, 1, 2, 3. And the marking function comes along for the ride. So this is, sorry, my notation I think was throwing things off a little bit. This is the edge contraction by edge labeled I. Okay, great. Any other questions? All right, so let me just write down, but then leave as an exercise that if, oh, okay, so let me define, sorry about my ugly board right now. Let me say that G is, let me say that a marked graph, stable and connected, is alternating if its automorphism group, when regarded as acting on the edge set, factors through the alternating subgroup of the symmetric group on this set of edges. So I discussed very quickly the fact that if GM is not alternating, then it zeroes out in the graph complex because it's identified under the relations we discussed with its negative. So let me just assert, and you can think this through if this is new material for you, that G upper GNP, this graded, this vector space in degree P, has a basis, or yeah, let me just write it like this, has dimension equal to the number of alternating stable graphs, stable connected graphs of type loopless, I suppose. Graphs of type Gn with exactly p+1 edges. And this is a finite number, which is a corollary of the previous assertion that all in all, there are only finitely many isomorphism classes. Okay, this will be explored more in the exercise session tomorrow.
Is there any geometric description of having an automorphism group that factors through?
I think that this is no. I don't know of such a thing. I think that like this connection makes the definition of having an alternating graph something that's quite interesting. I don't think that this is the kind of thing that you see graph theorists study, but they should. That's my take on it. Yeah, thanks. Anything else? Okay, so here's the main proposition, which is the reason that we are studying this at all. It's that the top weight Euler characteristic, so top weight in the sense of the weight filtration, in the sense that is discussed for weeks and weeks in the Stegosaur seminar. So the top weight Euler characteristic of MGN is exactly identified with the Euler characteristic of this n-marked genus G Kontsevich graph complex. So that is to say, explicitly, this Euler characteristic is the sum over all p's of the dimension of G and P sub P. And there's so much to say here, but I kind of don't want to. So what we're saying much more generally is that this graph complex sort of computes, in fact, the top weight cohomology of the space MGN. And you may have seen this in some form in Stegosaur if you're following that part. It goes through, so this proposition, I guess, is in my work with Soren Glatius and Sam Payne. What to say about it? So I'm sort of suppressing a lot of the beautiful geometry, but roughly speaking, the proof goes through.
Melody, I think there's a typo in that sum and the superscript of the.
Oh, that's really funny. I think that's because, thank you. Yeah. I'm just used to GNP from the probabilistic model. So I think my brain was there. Thanks. Yeah, so this graph complex is it can be identified by an identification with the cellular. Okay, so actually I should say it's not quite an identification, it's a quasi-isomorphism, meaning a map of chain complexes inducing isomorphisms on homology groups, so a quasi-isomorphism with the cellular chain complex of the moduli space delta Gn of tropical curves of genus G with n markings, and volume 1, meaning total edge length 1. I say that just to make the connection to last week's lectures. So last week you saw tropical moduli spaces MGN trop, and delta Gn is just the volume 1 slice of MGN trop. And moreover, this moduli space delta Gn is identified in work of Abramovich, Caparasso, Payne with the boundary complex of MGN inside the Deligne-Mumford-Knudsen compactification of bistable curves MGN bar. And then the machinery that you are learning about in Stegosaur then identifies the homology, the rational reduced homology of this boundary complex up to a degree shift with the top weight cohomology of the open moduli space MGN being compactified. So that whole sort of like litany of translations is what's behind this proposition. And again, right now I'm choosing to sort of take this as true and to explore the sort of combinatorial side. When you tunnel through from the algebraic geometry to the combinatorics, then what do you look at? That's what I'm doing in this series of lectures. So by the way, I had stated this proposition as an equality of numbers, like literal topological Euler characteristic, but better would be to make it a statement about equality of virtual SN representations. That is to say, SN, the symmetric group on n letters, is naturally acting, well, on the graph complex by permuting marked points, as well as on MGN, again, by permuting marked points. So this equality carries through SN equivariantly. In other words, these vector spaces, GGNP, should be understood as SN representations. And everything goes through on the level of SN representations. Basically because everything in sight is SN equivariant, it respects the SN action. So this proposition is also true on the level of virtual SN representations. Namely, this top weight Euler characteristic of MGN can be identified with the Euler characteristic of GGN as an element of the Grothendieck group of SN, finite dimensional SN representations. So in other words, formal Q linear combinations of representations of SN up to isomorphism. Is it okay? And that's, okay, so, and that's what we want to calculate. So,
sorry,
yeah,
but
sorry.
it's still a quasi-isomorphism of SN reps. Is that what you're saying?
That's not what I was intending to say. What I'm trying to say is like,
I mean, that identity of Euler characteristics comes from a quasi-isomorphism, right?
oh yeah, absolutely. You're right. And like everything in sight is SN equivariant. So if you just remember how SN is acting on everything, then you get a stronger identification. That's all I meant to say. Yeah, totally. Okay, so that's what we'll be studying. So our goal is to prepare ourselves to state the main theorem, which is, so I think the statement will come next time, but the statement, let me tell you what the main theorem is saying, and then I will define what I need. The main theorem is on the Frobenius characteristic of the top weight Euler characteristics of MGN for each fixed G. And my goal today is to just explain to you what Frobenius characteristic is, because this is something that I would be delighted for everyone to know. And then next time I'll explain our formula for Frobenius characteristic. So basically what it is the following, like look, all right, so suppose I fix G, and I'm interested in all top weight Euler characteristics of MGN at the same time for all n's. So that means that for every value of n, I'm interested in a representation of Sn, or more precisely, a virtual Sn representation, possibly some Q-linear combination of Sn representations with plus or minus coefficients, just because they arose as an Euler characteristic. So the Frobenius characteristic is just packaging for a sequence of Sn representations, one for each n. It knows exactly as much as data, but it's a very good way to package it all in terms of one big completed symmetric function. So that's the goal of the next few minutes. So let me tell you, or remind you, depending on where you are with this, what Frobenius characteristic means. And this last bit of the talk is logically separate from the rest of it. So let me remind you, or let me inform you, you can black box this, that the irreducible representations of the symmetric group on n letters are in bijection with partitions lambda of n. Do you know what I mean by a partition? Just a non-increasing sequence of positive numbers adding to n. And so I'll write V sub lambda for the Specht module, the irreducible representation corresponding to lambda. Okay. And suppose I have a sequence of virtual representations of Sn, Wi, a virtual representation of Si. So here, let me just write it, Wn, you can think of it as a isomorphic to a direct sum of these irreducibles. So the sum over C sub lambda, V sub lambda, where the C's are just rational numbers. Sorry, let me start over. So if you have some sequence of virtual representations of Sn, then up to isomorphism, they look like formal linear combinations, C lambda, V lambda. And I want some way of remembering them all at once in one gadget. That's what a Frobenius characteristic is. Okay, so we will do this as follows. Let me just write that down so you see what so I've recorded what the logic here is. So now let me review or tell you the basic definitions of symmetric functions. So let me write lambda for the ring of symmetric functions that's so central to much of algebraic combinatorics. So this is the limit in the the inverse limit in the category of graded rings, of the ring of polynomials in n variables that's invariant under permutations of variables. So this is the ring of symmetric functions. And it has lots of elements. So I'll just write down a random element just to see what it looks like. So I might have an element of the form x1 times x2 squared plus x1 squared x2. So it's a, I don't know if you've never seen this before, it's a funny name because these things aren't really polynomials. People talk about them as symmetric polynomials, but they're power series in some sense with infinitely many variables because they have to be invariant under permuting any finite set of variables. So this dot, dot, dot is crucial here. And there are famous subsets of the symmetric functions. So let's recall, or I'll just tell you, you can black box, that the Schur functions S lambda, as lambda ranges over all n, are a basis, they're a Z module basis for the degree n homogeneous part. So for lambda n, the degree n homogeneous part. And it's okay if you haven't seen the definition of a Schur function. A Schur function is a generating function for a semi-standard tableau of shape lambda, but they form a basis, this is well known in combinatorics, for the degree n homogeneous part as lambda ranges over all partitions of n. And there are, like combinatorialists know, like, 5 at least different bases, at least after tensoring with Q, that are very natural and all very important. So the Schurs are one of them. Another one is the power sum symmetric function. So let me define the power sum symmetric function p sub I is just the sum of the ith powers. I should say this one is visibly symmetric under permuting the variables. The Schurs are not visibly symmetric. You have to prove a proposition that says that they're symmetric. This is the power sum symmetric function. And now having defined p sub I for all non-negative integers I, let me define p sub lambda. So if lambda is a partition, lambda 1 through lambda 2, and so on. And p sub lambda is by definition the product, p lambda 1, p lambda 2. Sorry, this is finite. P lambda k. So then recall again that the p lambdas are also a basis, at least after tensoring with Q. And before going further, it will be useful to define the so-called inhomogeneous power sum symmetric functions. This is but a bit of notation. So capital Pi, oh, sorry, I feel like I haven't distinguished my capitals and lower cases very well. So this capital Pi is just 1 plus little pi. This is called the inhomogeneous power sum symmetric function. Okay. I've told you a bunch of facts so far. Is it okay? You can, I don't know, push back just as much as you want. So the point is, like, look, if you want to sort of compile all your information about your virtual SN representations, by what you know about the decomposition of finite dimensional representations into irreducibles, you just want to be able to remember, like, a rational number associated to each lambda. And you can do that by packaging that into a gigantic symmetric function, albeit one that occupies infinitely many degrees, degree 1, degree 2, degree 3, and so on. So in order to do that, I'd better define the sort of degree completion, lambda hat. This is the inverse limit of, one way to define it is the inverse limit of these rings of power series, the degree completion. This is the degree completion of lambda. So this is a little bit subtle. It's hard to see from the definitions, but in the ring lambda, your elements are only allowed to occupy finitely many degrees, whereas in lambda hat, they can occupy infinitely many degrees. This is the degree completion. Okay so far? If so, I will just write the definition of Frobenius characteristic. Okay. So if W is a finite dimensional Sn representation, then its characteristic, or Frobenius characteristic, is the following symmetric function. Okay, there are two ways to define it, and I claim they're the same. So I'll denote the characteristic, first of all, by ch of W. And the first way to define it is just as a formal sum of S lambdas. Here lambda ranges over partitions of n, where W is isomorphic to a formal sum C lambda V lambda. So that's the first way to define the characteristic. And the second way is to define it as the following. So it's normalized by dividing by n factorial. It's the sum over sigma and Sn of the trace of sigma with respect to the representation W times psi of sigma. So here, psi of sigma is a symmetric function. It's the following symmetric function. It's the product PA1 up through PAL, where the AIs constitute the cycle decomposition, the cycle type of sigma. So sigma has cycle type with cycles of length A1 through AL. Okay. This is the definition. If you've never seen it before, there are a couple of things to note. Number one, I defined it twice. So there's a lemma that these are equal. And this lemma is combinatorially equivalent to the fact that the transition matrix between the Schur and the powers and symmetric functions is exactly the character table of Sn, which is sort of well known in algebraic combinatorics, but is beyond the scope of my brain at the moment. It's certainly beyond the scope of this talk. But in any case, something like this, that something like this is true is not implausible. We're just saying, like, look, you want to encode this virtual Sn representation here, this C lambda is just rational numbers. You want to encode it as a symmetric function, you can do so. For example, just remember the C lambdas by attaching them as coefficients of the Schur basis. Or alternatively, as is well known, representations are determined uniquely by their characters. So just remember their characters by attaching them to the appropriate P basis. Okay? Okay, and then the last thing to do is just to note that if you have a sequence of, sorry, I guess I should have said, I defined this just for a single finite dimensional Sn representation. So it would have decomposed as a direct sum of irreducibles. Maybe I should write it better like this, with V lambda appearing with multiplicity C lambda. But now just extend linearly to obtain the general definition of Frobenius characteristic. So this is the last thing we'll do today. So, similarly, if you have a sequence of virtual Sn representations, these are all finite dimensional. Sorry, everything here is finite dimensional. Then define the characteristic of W by extending linearly. So now this is an element in lambda hat. Okay? So what I wrote in the notes is that ch of W knows W and W knows ch of W, right? It's just a packaging device, but it's a fairly good packaging device because, for example, if you have a sequence of Sn representations that deserve to be related to each other, then sometimes the entire Frobenius characteristic has a nice form. And that's going to be the case of interest in this series of talks, which is the sequence of top weight Euler characteristics of MGN understood as Sn, virtual Sn representations. So next time we'll start with the statement of the main theorem. So next time, sorry, not next today. Next time we'll state the main theorem, which is on the Frobenius characteristic of top weight Euler characteristic of MGNs. So this is again for fixed G and N all at once. Okay. Yes.
So if I'm going to get some kind of characteristic that lives in that completion, then I would assume that, like, this sequence of representations, if I truncate them, then they should all be the same representation up to truncation, so that I actually have something that'll live in that completion. I mean,
no, the completion is just, it's kind of like, it's just formal. It's akin to allowing power series instead of polynomials.
I see. I can just...
The array of symmetric functions, the way I defined it, hopefully I did it carefully enough, elements are sort of power series in infinitely many variables that are symmetric upon permuting the variables and have bounded degree. Lambda hat just drops that. So if you have, like, infinitely many representations, you just want to pass to lambda hat to encode everything. But ch of W is, again, it's exactly the data of W, nothing more, nothing less.
I don't know. It seems like there's some kind of, what if I just have the same representation over and over again? And then so all I do is like make the coefficient of that thing bigger and bigger. So
I'm allowing you to tell me for each N an Sn representation. So I don't know what you mean by same representation again and again. Like maybe you mean like trivial in each degree. I mean, yeah, you could give me jump, like you could give me a sequence of representations that are completely unrelated to each other, and then it's unrealistic to expect a nice formula for the Frobenius characteristic. But in the case in this talk, that's, the representations are related to each other closely. And in the exercise session, there will be a really cool, I think, problem about computing ch of, so on the exercises tomorrow, you compute the characteristic of W, where W sub n is h naught of conf n of S1. This is the kind of situation where, like, look, it's just configuration spaces of n points on a fixed topological space on S1, namely. It's not unreasonable to hope for some nice formula that captures all of these Wn's at once.
Thank you. Are there other questions for Melody?
Yes, that's right. Over all n, so you have to make sure to be in, oh, sorry. The question is ch of W the sum of all the ch's of Wn? Yeah. You just have to sort of make sure to pass to the degree completion of lambda to accommodate them all at once, so to speak.
All right. Are there any more? Oh, here you go. Do you see that question, Melody?
Yeah. You mentioned that, so the question is, you mentioned that graph theorists should think about these types of objects. Why is that? What is interesting to them here? I mean, I don't know. It's not meant to, I just invite more people to think about graphs in this interesting way, I mean, I don't know. It seems to me that, asking for a friend, literally, why do graph theorists study what they study? I think, very, very roughly speaking, they often study things because of deep connections to sort of like large data structures, like data science, computer science. But here we are embarking on a study of graph theory as it relates vaguely, roughly speaking, to physics. I think it has a completely different flavor. So for example, all the counting problems that we'll embark upon next time in some detail will be groupoid counting problems where objects deserve to be counted inversely proportional to the number of automorphisms they have. This is the kind of thing that is very natural in physics that you don't quite see so much in sort of computer science-y type applications of graph theory. How is that? Okay, great. Okay, question, can I say more about the proposition that lets me restrict to graphs with no weights on the vertices? Okay, so let me just state a proposition. I think that this proposition won't be self-contained because of lack of time, but I'll state a two-part proposition that's true. You can see a paper with myself, Soren, and Sam. We have several papers. It's the one that starts where the title has marked points in it. Okay, so the proposition is as follows. Delta GNW, which I'll define in a moment, is contractible. This is for the correct range. I can't remember, maybe like, let's just say G is at least 2. And the second is that the following delta GNLW, which is something, is contractible. So now I need to tell you, I'm going to define certain sub-loci of the moduli space of genus G n marked curves of total volume 1. So the first here, which I've denoted upper W, is the one that parametrizes tropical curves with containing a vertex of a positive weight. And the second is a larger locus. It hits everything. It contains all tropical curves with a vertex of positive weight or a loop, or both. So, you know, since we're only talking about Euler characteristics, I could have been more conservative and said, well, there are certain subcomplexes of a slightly larger graph complex where the generators have either a vertex or a vertex of positive weight or a loop. And these subcomplexes are acyclic. They have no homology. But actually a stronger thing is true, which is that the actual, the space, the moduli space, sort of a subcomplex of delta Gn is in fact a contractible topological space. Great. Question, let's see. Oh, volume 1. Okay, sorry, the question was, what does volume 1 mean? So all I was saying is the following. So you saw from Margarita a certain moduli space, MGN trop, which is, you know, you got the whole definition. It was, sorry. So as a set, this is isomorphism classes of tropical curves of type Gn. And then as a space, you could naturally see it. You saw this last week, that it was made of cones, basically. Because for every fixed combinatorial type, sorry, my tablet has done something weird. So let me avoid the right-hand side of my tablet. I can't write on that at the moment. So for any fixed combinatorial type, like I know this one, say, you obtain a cone parametrizing the possible edge lengths, which are just sort of any positive real numbers, alpha and beta in this case. So here you obtained, in Margarita's talk, you would see that you obtain actually half a cone because of the automorphism that switches alpha and beta. But whatever, it's still a cone. And then this whole space is built out of cones. So this space, MGN trop, as a topological space, is contractible because it's made of cones. You just shrink everything down to a vertex. So if you are to have, oh, here we go. If we are to have any hope of an interesting space topologically, you had better slice that generalized cone complex with a sphere, namely parametrizing those tropical curves with the total edge length. So if the underlying graph is G, and there's a length function on the edges. Sorry, and in Margarita's setting, you have a weight function too, which did not come up in today's talk. Then volume 1, sorry, this is a long answer, means that the sum of the edge lengths is exactly 1. Yeah, so in this picture, it would have been a slice, a volume 1 slice. That red part. Okay, great.